All right, let's get right into it. When you picture a train, what comes to mind? The huge engine, right? Or maybe that long line of carriages. But you know, the real unsung hero of the entire railway is the wheel. It looks so simple, doesn't it? Just a circle of steel. But it's actually an incredible piece of precision engineering, where every single millimeter counts.
And I'm not kidding when I say every millimeter. We're talking about massive forces, 1,000 tons of steel, hurtling down a track at high speed. The margin for error is practically zero. A tiny flaw, something you couldn't even spot from a few feet away, could literally lead to a catastrophe. The stakes are just unbelievably high. So just how small are we talking? Get this, on the very same axle, the diameter of the two wheels can't differ by more than half a millimeter. That is about the thickness of 5 strands of your hair. That is an insane level of precision, and it's absolutely vital for keeping that train running smooth and safe.
Okay, so before we dive into all the things that can go wrong, we really need to understand what right looks like. So let's break down the anatomy of a brand new, perfectly made train wheel.
You'll see that every single part of this wheel has a very specific job. The tread, well, that's the part that actually rolls on the rail. That little lip on the inside, that's the flange. And its job is to make sure the wheel doesn't just slip right off the track. And then the web connects the whole thing to the axle, giving it incredible strength. It's a simple but really effective design.
But here is the real secret sauce. The absolute genius of the train wheel is the 1 in 20 taper. See, the tread isn't perfectly flat. It's actually shaped like a very slight cone. And that tiny little angle, it's probably one of the most important and brilliant features in all of railway engineering.
So how on earth does that work? Well, because of that taper, if the wheels start to drift a little to one side, the part of the wheel touching the rail on that side gets effectively wider while the other side gets narrower. This tiny difference in diameter makes one wheel turn slightly faster than the other, which naturally steers the whole thing right back to the center of the track. It's this amazing self-correcting system that cuts down on friction, gives you a smooth ride, and even helps the train get around curves. It's just pure physics in motion.
But, of course, that perfect shape doesn't last forever. The constant fight against weight, friction, and just immense forces eventually wears that perfect profile down, creating some really dangerous defects. So, let's meet the villains of our story. And our first bad guy is called the sharp flange. This happens over time as that nice rounded edge of the flange wears down, getting thinner and, well, sharper, almost like a blade.
Now, to check for this, inspectors use this special tool, a tire defect gauge. On a good wheel, you can see there's a clear gap. The flange has its proper rounded profile. But as it wears down, that gap starts to disappear. And once the flange fits perfectly snug against that gauge, it's become dangerously sharp. That wheel has to be taken out of service.
So why is a sharp flange so bad? Well, it basically acts like a knife, especially when the train goes over a point, which is that part of the track that switches it from one line to another. Instead of being guided smoothly, that sharp edge can actually try to climb the rail and force its way onto the wrong track. And that, as you can imagine, can lead to a derailment.
All right, next up in our rogues gallery is the deep flange. This defect happens when the tread wears down, which makes the flange seem taller, or deeper, compared to the surface it's rolling on. To put that in perspective, a brand new wheel flange is about 28.5 millimeters high. But if wear causes that height to creep up past 35 millimeters, it's crossed a critical safety threshold. The wheel is now a danger and has to be condemned.
The problem here is purely physical. A flange that's too deep can actually start hitting parts of the track infrastructure, what they call the permanent way. You know, all the metal plates and bolts holding the rails together. At high speed, that kind of impact can shatter those components and, once again, cause a catastrophic derailleur.
And there are plenty of other ways a wheel can go bad. You can get a flat tire. And no, it's not from a puncture. It's from the brakes locking up and the wheel skidding, which grinds a flat spot on it. That creates this horrible hammering impact with every single rotation. Then there's the hollow tire, where the middle of the tread wears down faster than the edges. This completely ruins that perfect 1 in 20 taper, and the wheel loses its ability to self-center.
So, with all these things that can go wrong, how do railways keep their trains safe? Well, it all comes down to this relentless, meticulous process of inspection and repair. Let's take a look at how they find and fix these flaws.
After a super detailed inspection, the wheels are basically sorted into 3 repair categories. Most of them just need a normal repair, where they're put on a lathe and machined back to that perfect profile. But if the axle itself is bent or damaged, it's a full axle replacement. And if the wheel itself is cracked or just too worn down to be reshaped, it gets tagged for a disc replacement. And replacing a wheel is an absolutely incredible process. First, they machine the hole in the new wheel and the spot on the axle to unbelievably exact measurements. Then, both surfaces get coated with this special mix of lead and linseed oil. And finally, a massive 500-ton hydraulic press forces the wheel onto the axle. The fit is so tight, it's like they become a single piece of steel. They even monitor the pressure on a graph to make sure the fit is 100% perfect.
We've spent a lot of time on the wheels, but they're mounted on something that's just as important, the axle. So let's turn our attention to this unseen core that holds everything together.
And just like the wheel, every part of the axle is engineered for a purpose. The journal at the end is where the bearings sit, letting everything rotate smoothly. The wheel seat is that super precisely machined section we just talked about where the wheel gets pressed on. And the body is the main shaft that has to handle all of those immense twisting and bending forces.
So how do you find a flaw that you can't even see? A tiny crack could be forming deep inside that solid steel axle. To find them, technicians use ultrasonic testing. They send high-frequency sound waves through the metal and then listen to the echoes that bounce back. Using all these different scanning techniques, they can build a complete 3D picture of what's going on inside the axle and catch a hidden defect before it ever becomes a failure.
Besides those invisible internal flaws, axles can also get physically damaged on the outside. If an axle is even slightly bent, or if it gets a deep scratch, a notch, or even just some corrosion pits, it has to be replaced immediately. The risk of it snapping under all that weight is simply too high.
You see how it all connects? From the subtle genius of that 1 in 20 taper to the invisible sound waves of an ultrasonic test, all the way to the brute force of a 500-ton press. Every single one of these details is part of a complex system, and that system is engineered for one single purpose: to keep you safe.
It's so easy to just take that smooth, rhythmic click-clack of a train ride for granted, isn't it? But it's not an accident. It's the sound of some of the most incredible engineering on the planet working exactly as it should. So maybe the next time you're on a train, you'll listen a little closer and think about those amazing wheels of steel doing their job flawlessly right beneath your feet.